Imagine trying to understand the entire history of your family by looking at a single photograph. Not just your parents and grandparents, but every ancestor stretching back through thousands of generations, all the way to the very first humans who ever lived. The depth of time involved would be almost impossible to grasp, wouldn't it? Now imagine trying to understand not just human history, but the history of everything. Every star that has ever shone, every planet that has ever formed, every atom that has ever existed. 13.8 billion years of cosmic history compressed into a story we can somehow hold in our minds. Tonight, we're embarking on perhaps the most ambitious journey we've ever taken together, a voyage through the entire history of the universe, from its very first moment to this present second as you listen to these words. We're going to compress those 13.8 billion years into the span of a single day, from midnight to midnight, creating a cosmic clock that will help us understand our place in this vast, ancient story. Hello, and welcome to the Sleepy Astronomer. If you're settling in for the first time, welcome aboard our gentle drift through deep time. And if you've travelled with me before through the quiet corners of space, it's wonderful to have you back for this ultimate journey. Whether you're tucked up in bed, curled up in a favourite chair, or perhaps lying somewhere you can see the stars through a window, I'm so grateful you're here to witness the universe's biography with me. Our cosmic day begins at the stroke of midnight, not the familiar midnight of Earth's rotation, but a far more profound midnight when time itself began, at 0000000, in a moment that defies all our everyday understanding. The universe erupted into existence. By dawn, the first atoms will have formed. By mid-morning, the first stars will ignite. Galaxies will dance across the afternoon sky, and our own solar system won't appear until well into the evening hours. And humanity, we arrive in the very last second before midnight strikes again. This metaphor of a cosmic day isn't just a clever way to organize vast stretches of time. It's a meditation on patience itself. The universe has been unfolding its story with a patience that spans eons, each chapter building carefully on the last. Ancient cultures understood cyclical time, the great wheels of seasons and generations, but the universe's story is both cyclical and linear, patterns repeating at ever greater scales, yet always moving toward something new, something more complex, something more beautiful. There's something deeply humbling about setting our cosmic clock this way. All of recorded human history, the rise and fall of civilizations, the writing of every book, the composition of every symphony, the love stories and heartbreaks of billions of people, all of it fits into the final second of this cosmic day. Yet there's something equally inspiring about it. That final second represents the moment when the universe became aware of itself, when matter organized itself into patterns complex enough to contemplate its own existence. Tonight, as we journey through this cosmic day together, we'll witness the patient birth of atoms and stars, the slow dance of galaxies across billions of years, the delicate formation of planets, and the miraculous emergence of life. We'll see how every element in your body was forged in the nuclear fires of ancient stars, how the carbon in your cells and the oxygen in your lungs are the gift of stellar generations that lived and died long before our sun was born. So find your most comfortable position, whether you're drifting towards sleep or settling in for a long journey through time. Take a deep breath and let yourself sink into the rhythm of cosmic time, where moments stretch into millennia, and billions of years pass like the turning of pages in an ancient book. The clock is approaching midnight, the universe is about to begin, and we are about to witness the most extraordinary story ever told, the story of how everything we know came to be, written in the patient language of physics and time, told in the gentle whisper of expanding space and cooling stars. Let's begin our cosmic day. Midnight strikes. In that first moment, a moment so brief it defies every metaphor we might reach for, the universe begins, not with a bang despite what we call it, but with something far more mysterious. There was no explosion in the sense you might imagine, no great thunderclap echoing through space because there was no space yet to echo through. There wasn't even silence because silence requires the absence of sound, and sound itself had not yet been invented. Picture this if you can, at the very stroke of midnight on our cosmic clock, everything that will ever exist, every star that will ever shine, every planet that will ever form, every thought that will ever be thought, all of it compressed into a point smaller than the smallest thing you can imagine. And then, in the first tiny fraction of a second, smaller than the time it takes light to cross an atom, everything changes. We call this moment t equals 0, though even calling it a moment is stretching language past its comfortable limits. This is the Planck epoch, named after the physicist Max Planck, and it lasts for what scientists call Planck time, about 10 to the minus 43 seconds. To put that number in perspective, there are more Planck moments in a single second than there are seconds in all the billions of years since the universe began. It's a time frame so impossibly brief that our physics, all our carefully constructed equations and theories, simply throw up their hands and admit defeat. During this first infinitesimal instant, the four forces that will govern everything, gravity, electromagnetism, and the strong and weak nuclear forces are still unified into one. Temperature isn't just hot, it's infinite. Density isn't just extreme, it's beyond measurement. The very concepts of space and time are crystallizing from something even more fundamental, something quantum physicists call the foam of space-time itself. And then, still within that first second, inflation begins. This is where the universe pulls off perhaps its most impressive magic trick. In a period lasting only about 10 to the negative 32nd seconds, a time span that makes our previous impossibly brief moment look leisurely by comparison, space itself expands by a factor that's almost comical in its enormity. We're talking about the universe growing by at least 10 to the 26th power times its original size. To put this in terms that might make you smile, imagine a grape expanding to the size of Earth in less time than it takes light to travel the width of a proton. Why did this happen? Honestly, we're still working on that one. The best theories suggest that space itself was filled with something called an inflaton field, a kind of energy that wanted very badly to push everything away from everything else. Think of it as the universe's most enthusiastic personal space advocate, insisting that even the tiniest particles needed much, much more room. This inflationary epoch is where many of the universe's future personality traits get locked in. The quantum fluctuations happening during this period, tiny random jitters in the fabric of space itself, will eventually become the seeds around which galaxies form. Every cluster of stars you can see in the night sky, every cosmic web of matter stretching across billions of light years, traces its ancestry back to microscopic ripples in space-time during those first 10 to the minus 32nd seconds. As inflation finally begins to wind down, and we're still talking about times measured in fractions of seconds, something equally remarkable happens. The inflaton field that drove this cosmic expansion begins to decay, and as it does, it transforms into the matter and energy that will populate the universe. It's a bit like watching a cosmic firework, where the initial burst of light fades and transforms into all the different coloured sparks that fill the sky. But what emerges isn't the familiar matter we know today. The universe at this point is still far too hot and energetic for anything as mundane as atoms. Instead, we have a soup of fundamental particles, quarks, leptons, bosons, all dancing in a bath of radiation so intense it would make the core of the sun seem like a gentle campfire. As our cosmic clock ticks past those first few microseconds into the first few minutes, the universe continues to expand and cool. This is crucial because temperature in the early universe is everything. When the universe is unimaginably hot, particles have so much energy that they can't stick together. As it cools, though, different kinds of structures become possible, like a liquid cooling enough for crystals to form. Around 10 to the minus 12 seconds after midnight, still well before we've even reached the first minute of our cosmic day, something called electro-weak symmetry breaking occurs. This is when the electromagnetic force and the weak nuclear force, which started as a unified electro-weak force, decide to go their separate ways. It's a bit like watching conjoined twins gradually developing into distinct individuals, each with their own personality and role to play in the cosmic drama. By the time we reach 10 to the minus 6 seconds, 1 microsecond, quarks begin to combine into protons and neutrons, the building blocks of atomic nuclei. This is called the quark epoch, and it's where the universe first begins to assemble the pieces from which everything else will eventually be built. Imagine the cosmos as a cosmic construction site, and these first particles as the raw materials being delivered. The universe is still incredibly hot at this point, about 1 trillion degrees Kelvin, which makes the centre of our sun look positively Arctic by comparison. But it's cool enough for protons and neutrons to survive without immediately being torn apart by the intense radiation surrounding them. For the next few minutes, and this is where we finally start measuring time in units that feel almost familiar, the universe undergoes what's called Big Bang nuclear synthesis. This is the cosmic forge where the first atomic nuclei are assembled. Protons and neutrons, still bathed in intense heat and radiation, begin to stick together to form the nuclei of the lightest elements: hydrogen, helium, and just a trace of lithium. Most of what forms is hydrogen, simple, elegant, just a single proton. About 25% becomes helium, with its 2 protons and 2 neutrons, making it the universe's first example of nuclear engineering. The tiniest fraction becomes lithium, and that's it. The universe, at this point, has no carbon, no oxygen, no silicon, no iron, none of the heavier elements that will eventually make planets and life possible. Those will come later, forged in the nuclear furnaces of stars that won't exist for millions of years yet. Think about this for a moment. The hydrogen in the water you drink, the helium in those party balloons that seem to have a mind of their own. These were born in the first few minutes of cosmic time. Every drop of water on Earth contains hydrogen nuclei that formed when the universe was only minutes old, in temperatures that would vaporize any material we know today. As we approach the 3-hour mark on our cosmic clock, about 20 minutes in real time after the Big Bang, the universe has cooled enough that nuclear reactions stop. The cosmic forge goes quiet. From this point forward, the ratios of hydrogen and helium will remain essentially unchanged until the first stars form, hundreds of millions of years later. The universe has set its basic chemical composition, and it's a minimalist masterpiece, about 75% hydrogen, 25% helium, and traces of lithium. Everything else, every element that makes a planet rocky, every element that makes life possible, is still waiting to be invented. But here's where the universe plays another of its patient games. Even though we have atomic nuclei, we don't yet have atoms. The universe is still far too hot for electrons to settle down and orbit these nuclei. Instead, we have what's called a plasma, a hot ionized soup where electrons zip around freely, unable to find a nuclear home to settle into. This plasma has an important property. It's opaque to light. Photons, particles of light, can't travel very far before they bump into a free electron and get scattered in a new direction. It's like trying to see through fog so thick that even the most powerful lighthouse beam gets lost within a few feet. The universe has matter. It has energy. But it doesn't yet have the transparency that would allow light to travel freely across cosmic distances. Imagine the universe at this stage as a cosmic hall of mirrors, where every photon of light bounces endlessly from electron to electron, never able to travel in a straight line for more than the tiniest fraction of distance. The light is there, brilliant, intense light carrying enormous energy, but it's trapped in an eternal game of pinball, ricocheting through the dense soup of particles that fills all of space. This is profoundly different from the universe we know today, where light from distant stars can travel for billions of years across the emptiness of space to reach our eyes. In this early epoch, if you could somehow exist in this plasma, which you couldn't for reasons involving being instantly vaporized, you wouldn't be able to see your hand in front of your face, not because there was no light, but because there was too much of it, all scrambled and scattered in every direction. The temperature at this stage is still around 3000 degrees Kelvin, hot enough to melt copper, hot enough to make glass glow white hot. Every cubic centimetre of space contains more energy than our sun produces in a year. Yet despite this incredible energy density, despite the brilliant light trapped within the plasma, the universe remains dark to any hypothetical observer, shrouded in its own luminous fog. This opacity will persist for hundreds of thousands of years, until the universe cools enough for electrons and nuclei to finally combine into neutral atoms. Only then will the cosmic fog lift, and the universe will become transparent for the first time. When that happens, still hours away on our cosmic clock, the light that has been trapped and scattered for so long will finally break free, streaming across space for the first time. That ancient light still surrounds us today, cooled by billions of years of cosmic expansion into the faint microwave radiation we call the cosmic microwave background. But we're getting ahead of ourselves. For now, as we drift through these first hours, the universe remains wrapped in its brilliant, impenetrable veil. During these first 3 hours, something else equally remarkable has been happening. The universe has been writing its autobiography in the language of particle physics. Every interaction between particles, every quantum fluctuation, every tiny ripple in the fabric of space-time is recording the story of these first moments in ways that we can still read today, billions of years later. The cosmic microwave background radiation that we detect with our most sensitive instruments is like a baby photograph of the universe, capturing what it looked like when it was only 380,000 years old. But the ratios of hydrogen and helium created during these first few minutes serve as an even older record, a fossil from when the universe was mere minutes old. When we measure the abundance of these elements in distant stars and galaxies, we're essentially reading the universe's birth certificate. This is where the beauty of physics reveals itself most clearly. The universe isn't just a collection of random events, it's a story where every chapter builds on what came before, where the laws of nature themselves serve as both author and narrator. The temperature at any given moment determines what kinds of particles can exist, what kinds of interactions are possible, what kinds of structures can form. As the universe cools, it unlocks new possibilities, like a cosmic combination lock, where each degree of cooling reveals new secrets. For now, as we reach the 3-hour mark, the universe has accomplished something remarkable in its first few hours of existence. From a state that defied all description, it has expanded, cooled, and organized itself into the basic building blocks of everything that will follow. It has created space and time, established the fundamental forces of nature, and assembled the first atomic nuclei. It has set the stage for everything else. But perhaps most wonderfully, it has also established the rules that will govern all future creativity: the conservation of energy, the relationship between matter and space-time, the delicate balance between the fundamental forces. All of this is being determined during these first few hours. The universe is not just creating matter, it's creating the very laws that will determine how that matter can interact, combine, and organize itself in the eons to come. Think about the incredible specificity of what's happening. If the universe expanded just a little too quickly, matter would be spread so thin that gravity could never pull it together into stars and galaxies. If it expanded too slowly, everything would collapse back into a singularity before stars could form. If the ratio between matter and antimatter had been just slightly different, there wouldn't be enough matter left after annihilation to build a universe. If the fundamental forces weren't precisely balanced, protons couldn't hold together, or electrons couldn't orbit nuclei. The universe during these first hours is like a master craftsperson, not just creating the raw materials for everything that will follow, but also forging the tools that will be used to shape those materials. Every physical law, every constant of nature, every rule that will govern the behavior of matter and energy throughout cosmic history is being established with a precision that's almost impossible to comprehend. And yet, from our perspective, it would still be utterly alien. No stars shine in this universe because stars haven't been invented yet. No planets orbit because there's nothing to make planets from except hydrogen and helium. No life exists because the elements that make life possible, carbon, oxygen, nitrogen, phosphorus, are still unimaginable futures waiting to be forged in stellar cores that won't exist for millions of years. Even light, that most familiar phenomenon, can't travel freely through the dense plasma that fills all of space. But the patterns are there, hidden in the quantum fluctuations from the inflationary epoch, waiting to grow. The seeds of every galaxy, every star, every world, every living thing are already embedded in the fabric of space-time, so subtle they won't become visible for hundreds of millions of years. In the statistical variations of density from place to place, variations so tiny they amount to only about 1 part in 100,000, lie the blueprints for all the large-scale structure that will eventually fill the cosmos. This is perhaps the universe's most elegant trick, hiding infinite complexity within apparent simplicity. From outside, these first few hours might seem almost boring, just a hot, dense, gradually cooling soup of elementary particles. But within that simplicity lies the seed of everything beautiful and complex that will ever exist. Every spiral galaxy, every planetary system, every sunset, every symphony, every moment of consciousness, all of it encoded in the initial conditions set during these first few hours. There's something deeply moving about this early universe, so full of potential, so rich with possibility, yet so utterly unlike anything we know. It's a reminder that the most important moments in any story are often the ones that seem the most impossible to understand. The universe's infancy defies our intuition at every turn, Yet without this strange and wonderful beginning, none of the beauty that follows would be possible. As we drift past the 3-hour mark on our cosmic clock, the universe settles into what will be, by its standards, a relatively quiet period. The dramatic transformations of the first few hours are over. The fundamental forces have separated, the first elements have been forged, and the basic architecture of space-time has been established. Now comes the long, patient work of cooling and expansion, setting the stage for the next great chapter in the cosmic story. But even in this approaching calm, the universe carries within itself all the seeds of future wonder. Every atom that will ever form, every star that will ever shine, every planet that will ever dance around a sun, every living thing that will ever draw breath, all of it is already there, waiting in the quantum patterns written into the fabric of space, during those first extraordinary moments after midnight struck and everything began. The first dawn has broken over the cosmos, not with visible light, that's still trapped in the plasma, but with the light of possibility itself, illuminating a future rich beyond imagining. 3 hours have passed on our cosmic clock, and the universe is about to enter what cosmologists call, with a touch of medieval drama, the Dark Ages. It's a curious name for what might be the most important period in cosmic history, a time when everything that had been bright and energetic and chaotic finally began to settle into something like the universe we might recognize today. Imagine the universe at this moment as a vast concert hall after the symphony has ended. The dramatic crescendos of those first few hours, the thunderous inflation, the rapid-fire particle interactions, the cosmic forge of nucleosynthesis, all of that has faded into silence. The cosmic background radiation that fills all of space is slowly cooling, like the last warmth from a fire that's been banked for the night. And yet, in this apparent quiet, some of the most profound changes in cosmic history are about to unfold. As we drift past the 3-hour mark, the universe has cooled to about 3,000 degrees Kelvin, still hot enough to melt most metals, but cool enough for something extraordinary to happen. For the first time since those earliest moments, electrons can finally settle down and find homes orbiting atomic nuclei. It's like watching a cosmic square dance where partners who have been spinning wildly around the dance floor finally come together in stable pairs. When electrons combine with protons and helium nuclei to form the first neutral atoms, something magical happens. The universe, which has been opaque to light for hundreds of thousands of years, suddenly becomes transparent. The cosmic fog lifts, and for the first time, light can travel freely across space. This moment, occurring around what we call recombination, is when the universe takes its first clear breath. The light that breaks free at this moment, ancient photons that have been trapped in the cosmic plasma since the first few minutes after the Big Bang, is still all around us today. Cooled by billions of years of cosmic expansion, it now exists as the cosmic microwave background radiation, a faint whisper from the universe's infancy that fills every cubic centimetre of space. When you tune a television to an empty channel and see the static on the screen, about 1% of that snow is this ancient light, the universe's baby picture, still echoing through the cosmos. But here's where the Dark Ages truly begin. Once this first light breaks free and streams away into the expanding universe, there are no more light sources. None. The nuclear fires of the first few minutes have long since gone out. No stars exist yet to illuminate the cosmic darkness. The universe enters a period that will last for hundreds of millions of years, from hour 3 to hour 6 on our cosmic clock, where the only light comes from the slowly cooling glow of that ancient radiation, and even that is fading as the universe expands. Picture this cosmic landscape if you can. Vast reaches of space filled with nothing but hydrogen and helium atoms, slowly cooling as they drift through the expanding darkness. The temperature drops steadily from thousands of degrees to hundreds, then to mere tens of degrees above absolute zero. In the deepest reaches of intergalactic space, it becomes so cold that any liquid would freeze solid in an instant, any gas would condense and fall like snow. You might wonder what there is to say about such an apparently empty time. After all, if nothing much is happening, no stars forming, no light shining, just atoms drifting through the dark, what story is there to tell? But this is where the universe reveals one of its most subtle and beautiful secrets. In the apparent emptiness, in the seeming quiet, some of the most important construction work in cosmic history is taking place. Remember those quantum fluctuations from the inflationary epoch, those tiny ripples in the density of matter that were imprinted on the universe during its first fraction of a second. During the Dark Ages, these fluctuations finally have the chance to grow. Like seeds planted in fertile soil, the slightly denser regions of space begin to attract more matter through the patient pull of gravity. This is where dark matter, that mysterious substance that makes up about 85% of all the matter in the universe, but interacts with ordinary matter only through gravity, plays its starring role. While we ordinary folks made of protons and neutrons were busy being hot and energetic during those first few hours, dark matter was quietly going about its business of clumping together under the influence of its own gravity. During the Dark Ages, these dark matter halos grow larger and more massive, like invisible cities being built in the emptiness of space. They create gravitational wells, dips in the fabric of space-time where ordinary matter can begin to collect. Hydrogen and helium atoms, drifting through the cosmic dark, gradually find themselves drawn toward these invisible gathering points. The process is incredibly slow by human standards. We're talking about changes that take millions, tens of millions, eventually hundreds of millions of years to unfold. If you could somehow observe one of these dark matter halos during the Dark Ages, you would need to watch for geological ages to see any noticeable change. It's like watching a tree grow, but stretched across timescales that make the rise and fall of mountain ranges seem like brief flickers. And yet, this slow construction project is laying the foundation for everything that will follow. Every galaxy that will ever exist is taking shape during these dark centuries, not yet visible, but already predetermined by the gravitational architecture being built in the shadows. The cosmic web, that vast network of dark matter filaments that spans the observable universe, is weaving itself into existence, creating the scaffolding upon which all future structure will hang. There's something deeply meditative about this period of cosmic history. After the dramatic violence of the first few hours, the universe settles into a rhythm as patient and steady as the tide. Matter flows along invisible channels carved by dark matter, following gravitational currents that guide hydrogen and helium toward their cosmic destiny. It's like watching a river system form in slow motion, with streams of atoms converging into larger flows, which merge into greater torrents, all guided by the invisible topology of spacetime itself. The temperature continues to drop during these dark millennia. By hour 4 on our cosmic clock, the universe has cooled to about 60 Kelvin, colder than the coldest winter night on Earth. By hour 5, it's down to about 30 Kelvin, so cold that the air you breathe would liquefy and fall to the ground. And still, the cooling continues, the universe spreading its energy thinner and thinner across ever greater volumes of space. In this cosmic winter, something extraordinary is preserved: simplicity. The universe during the Dark Ages is remarkably pure. There are only 3 kinds of atoms: hydrogen, helium, and a trace of lithium. No carbon, no oxygen, no silicon, no iron. None of the dozens of elements that will eventually make planets and life possible. The periodic table, that grand encyclopedia of chemistry, contains only its first 3 entries. This chemical simplicity means that the physics of this era is in some ways easier to understand than what will come later. Without heavy elements to complicate the picture, without stellar radiation to heat and ionize the gas, the universe during the Dark Ages behaves according to relatively simple rules. Gravity pulls, matter flows, temperature drops. It's like reading the universe's instruction manual when it was still written in large, simple letters. But within this simplicity, complexity is being born. The dark matter halos growing throughout the cosmos aren't uniform. They have structure, hierarchy, patterns. Smaller halos merged form larger ones, which combine into still greater structures, building up the cosmic web from the bottom. It's like watching a city grow from scattered farmsteads to villages to towns to great metropolitan areas, all connected by invisible highways of dark matter. Some regions of the universe become particularly rich in these growing structures, places where the cosmic web is especially dense, where multiple filaments intersect, where the largest dark matter halos are forming. These will eventually become the richest galaxy clusters, the great cities of the cosmic web. Other regions remain relatively empty, the vast cosmic voids where very little matter ever collects, creating the empty spaces that give the cosmic web its spidery appearance. As we approach hour 6 on our cosmic clock, something is stirring in the depths of the cosmic dark. The largest dark matter, halos have grown massive enough and collected enough hydrogen and helium that conditions at their centers are becoming extreme. Gas is falling into these gravitational wells from all directions, colliding and heating up as it compressed. Temperatures that have been dropping for hundreds of millions of years are beginning to rise again in these special places. These are the seeds of the first stars, though they won't ignite for millions of years yet. But already the universe is beginning to wake up from its long slumber. The Dark Ages are drawing to a close, and cosmic dawn is approaching. There's something beautiful about the way the universe uses this quiet time. Like a master craftsperson who takes time to carefully prepare materials before beginning the real work, the cosmos spends these hundreds of millions of years organizing itself, creating the invisible infrastructure that will support all the drama and beauty that's to come. During these dark centuries, every galaxy that will ever shine is being sketched in dark matter. Every cluster of stars that will ever form is having its gravitational foundation laid. Every cosmic void that will separate the bright regions of the universe is being carved from the expanding darkness. It's a period of pure potential where nothing visible is happening, but everything important is being prepared. Ancient cultures understood the power of darkness in creation myths. In many traditions, creation begins not with light, but with a fertile void, a creative darkness pregnant with possibility. The Egyptian concept of Nun, the dark, watery chaos from which all things emerge. The Norse Ginnungagap, the yawning void that existed before the world was made. The biblical darkness upon the face of the deep before the first words of creation are spoken. The cosmic Dark Ages echo these ancient insights in the language of modern physics. This is not the darkness of emptiness, but the darkness of gestation, of patient preparation, of invisible forces organizing themselves for the creative explosion that's to come. It's the cosmic equivalent of the months a seed spends underground before it breaks through the soil into sunlight. And like those ancient creation myths, The Dark Ages remind us that the most important transformations often happen in silence, out of sight, in what appears to be emptiness, but is actually full of hidden activity. The universe during this period is like a vast workshop where the greatest project in history is being assembled in the dark, piece by invisible piece. As hour 6 approaches on our cosmic clock, that long preparation is almost complete. The first dark matter halos have grown massive enough to begin collapsing under their own gravity. Gas is flowing inward, heating up, reaching densities and temperatures not seen since those first few hours after the Big Bang. The stage is being set for one of the most important moments in cosmic history, the moment when the first stars ignite and the Dark Ages come to an end. But for now, the universe remains wrapped in its patient darkness, still and quiet and full of invisible promise. In a few more moments on our cosmic clock, the first light will break through this darkness, and the universe will begin to shine. But these dark hours have been just as essential as those bright moments to come. Without this patient preparation, without this slow gathering of matter into the right places, none of the beauty that follows would be possible. The Dark Ages are ending, but their gift to the cosmos is permanent. The invisible architecture that will support 13 billion years of stellar light, planetary formation, and eventually the emergence of minds capable of looking back through time and marveling at these quiet centuries when the universe learned how to organize itself from the darkness. 6 hours have passed on our cosmic clock, and the universe is about to experience its most dramatic transformation since those first moments after midnight. After hundreds of millions of years of patient darkness, of invisible construction work happening in the shadows, something extraordinary is stirring in the deepest gravitational wells scattered throughout the cosmos. The Dark Ages are about to end, not with a whisper, but with the birth of light itself. Imagine standing in the cosmic darkness of this moment, if such a thing were possible, surrounded by the vast, cold emptiness that has defined the universe for so long. The temperature has dropped to just a few degrees above absolute zero, cold enough that any breath would freeze instantly and fall like snow in the weak gravity of this ancient time. The only light comes from the fading glow of that primordial radiation from recombination, now stretched and cooled by the universe's expansion into a barely perceptible whisper of warmth. But something's been growing in this darkness. Those invisible dark matter halos we spoke of during the Dark Ages have been pulling in hydrogen and helium gas for hundreds of millions of years, and in the most massive of these structures, the gas has finally become dense enough and hot enough for something miraculous to happen. The first stars are about to be born. These aren't the familiar stars we see in our night sky today, those modest, well-behaved nuclear furnaces that burn steadily for billions of years. The first stars, which astronomers call population 3 stars with the somewhat backwards logic of science naming conventions, are monsters. While our Sun contains about 333,000 times the mass of Earth, these primordial giants could be 100 times more massive than our Sun, or even more. They're the cosmic equivalent of those spectacular, brief-burning candles that light up everything around them but consume themselves in the process. Why were these first stars so massive? The answer lies in the cosmic chemistry, or rather, the lack thereof. Remember, the universe at this point contains only hydrogen, helium, and a trace of lithium, the 3 lightest elements, born in those first few minutes after the Big Bang. There's no carbon to catalyze nuclear reactions, no oxygen to help gas clouds cool efficiently, no silicon or iron to provide the heavy elements that help regulate star formation in later eras. Without these heavier elements, what astronomers, with their characteristic flair for oversimplification, call metals. The collapsing gas clouds that will become the first stars can't cool down as efficiently as they will in later epochs. And when gas can't cool down, it can't collapse into smaller, more modestly sized stellar nurseries. Instead, it forms these massive, hot, brilliant giants that shine with the fury of dozens or even hundreds of suns. Picture the moment when the first of these stellar titans ignites. Deep within a dark matter halo that has been growing for hundreds of millions of years, hydrogen and helium gas has been falling inward under the relentless pull of gravity. As it falls, it heats up, compressed by its own weight until the temperature at the centre reaches about 10 million degrees Kelvin, hot enough for the nuclei of hydrogen atoms to overcome their natural reluctance to get too close to each other. And then, for the first time since those first few minutes after the Big Bang, nuclear fusion ignites. Hydrogen nuclei slam together with enough energy to stick, forming helium and releasing tremendous amounts of energy in the process. The first star begins to shine, and suddenly, for the first time in hundreds of millions of years, there is light in the universe. But this isn't just any light. These population 3 stars burn so hot and bright that most of their energy emerges as ultraviolet radiation, light so energetic it can tear electrons away from atoms, ionizing the gas around them and creating bubbles of hot, glowing plasma in the cold cosmic dark. It's like watching the first campfire being lit after a long, cold night, except this campfire is millions of times brighter than our sun, and its light can be seen across millions of light years. As more and more of these stellar giants ignite throughout the cosmos, and we're still talking about incredibly rare events, with perhaps only one star forming in a volume of space the size of our local group of galaxies, something profound begins to happen to the universe itself. The ultraviolet light from these first stars starts to ionize the neutral hydrogen and helium that fills all of space, beginning what cosmologists call the epoch of ionization. This is like watching the cosmic fog lift for a second time, but in reverse. During recombination, the universe became transparent when electrons combined with nuclei to form neutral atoms. Now, the intense radiation from the first stars is breaking those atoms apart again, freeing electrons to wander through space once more. But unlike the opaque plasma of the early universe, this new ionized medium is thin enough that light can still travel freely through it. The process is gradual, unfolding over millions of years as more and more stars ignite, and their combined radiation slowly transforms the universe from a place filled with neutral atoms to one filled with ionized plasma. Imagine bubbles of ionized gas expanding around each new star, growing larger and eventually merging with bubbles from other stars until the entire universe has been transformed once again. These first stars are living fast and dying young, cosmic James Deans burning through their nuclear fuel at prodigious rates. While our sun will shine for about 10 billion years, slowly and steadily fusing hydrogen into helium, these stellar giants consume their fuel so quickly that they can live for only a few million years. In the context of our cosmic day, they're like brilliant sparklers that flare to life and burn out almost immediately. But their brief lives accomplish something extraordinary. They begin the universe's first chemistry experiment since the Big Bang. In their nuclear cores, where temperatures reach hundreds of millions of degrees, hydrogen and helium are being transformed into heavier elements for the first time in cosmic history. Carbon appears, forged from the fusion of 3 helium nuclei in a process so delicate that it seems almost miraculous that it works at all. Oxygen forms from the fusion of carbon and helium, neon, magnesium, silicon, sulfur, all the elements that will eventually make planets and life possible are being created in the nuclear furnaces of these stellar alchemists. And then, after their brief but brilliant lives, these stars face a fate unlike anything in the modern universe. When a massive star today, one perhaps 20 or 30 times the mass of our Sun, reaches the end of its life, it explodes as a supernova, one of the most violent events in the cosmos. But these first stars, with their incredible masses, may have faced an even more dramatic end, collapsed directly into black holes, perhaps without exploding at all. Some, though, do explode, and their explosions are spectacular beyond imagination. When a population 3 star goes supernova, it releases more energy in a few seconds than our Sun will produce in its entire 10 billion year lifetime. The explosion hurls all those newly forged heavy elements, carbon, oxygen, silicon, iron, out into the surrounding space at speeds of thousands of kilometers per second, enriching the pristine hydrogen and helium of the early universe with the first traces of cosmic pollution. These supernova explosions serve as the universe's first delivery system for heavy elements. The carbon in your cells, the oxygen you breathe, the iron in your blood, none of these elements existed before the first stars lived and died. Every heavy element in the universe today can trace its ancestry back to the nuclear furnaces and explosive deaths of these primordial giants. But the first stars accomplish something else equally important. They begin the process of cosmic renovation. The energy they pump into their surroundings, through their intense ultraviolet radiation, their stellar winds, and their explosive deaths, starts to heat up and stir the gas in their dark matter halos. This makes it harder for the next generation of stars to form in exactly the same way, ensuring that future stars will be smaller, longer-lived, and more like the stars we see today. As we move through hours 6, 7, and 8 on our cosmic clock, this process accelerates. More and more regions of the universe begin to host star formation. The dark matter web that grew during the Dark Ages now becomes visible for the first time, outlined by the light of stars forming along its filaments and nodes. What had been invisible architecture is suddenly illuminated, like a vast city lighting up at nightfall. The first proto-galaxies begin to take shape during this period. Not yet the grand spiral and elliptical galaxies we see today, but smaller, more irregular collections of the first stars and the dark matter halos that host them. These early galaxies are chaotic, violent places, constantly being fed by streams of gas flowing in along dark matter filaments, frequently merging with their neighbours, stirring and churning as they grow. This is also when the seeds of the first supermassive black holes begin to form, whether they grow from the direct collapse of the most massive population 3 stars, or from smaller seed black holes that gradually accrete mass from their surroundings. These cosmic monsters begin their long journey toward becoming the engines that will power quasars and active galactic nuclei in later epochs. Throughout this period, the universe is being transformed from a simple, chemically pristine cosmos into something far more complex and interesting. The periodic table is being written for the first time, element by element, in the nuclear cores of these stellar pioneers. The first molecular hydrogen forms when newly created carbon atoms catalyze reactions between hydrogen atoms, providing a more efficient coolant that will eventually allow smaller stars to form. There's something deeply moving about imagining this cosmic dawn. After hundreds of millions of years of patient darkness, the universe finally begins to sparkle with light. It's not yet the rich tapestry of galaxies we see today, but rather a sparse collection of brilliant beacons scattered throughout the cosmic web, each one a nuclear furnace forging the elements that will make everything else possible. Ancient creation myths from around the world echo this moment of cosmic illumination. The Hindu tradition speaks of Surya, the solar principle that brings light to dispel cosmic darkness. Celtic mythology tells of Lu, the light-bringer whose festival marks the turning of the year toward harvest and abundance. In many Native American traditions, the stars were scattered across the sky by creator spirits to provide guidance and wonder for the earth below. These myths capture something profound about this moment in cosmic history, the sense that light is not just illumination, but transformation. The first starlight doesn't just make the universe visible, it fundamentally changes what the universe is, adding complexity, chemistry, and the potential for all the richness that will follow. The Zoroastrian tradition, with its emphasis on the cosmic struggle between light and darkness, perhaps comes closest to capturing the significance of this epoch. The first stars are indeed light conquering darkness, but not through violence or conflict. Instead, they represent the universe's natural tendency toward greater complexity and beauty, the way simple hydrogen and helium, given enough time and the right conditions, will inevitably organize themselves into nuclear furnaces capable of forging new elements. As hour 9 approaches on our cosmic clock, the transformation is well underway. The universe that was once filled only with hydrogen, helium, and darkness now sparkles with the light of the first stars. Heavy elements are being created and dispersed for the first time. The first proto-galaxies are taking shape. The cosmic web, invisible for so long, is beginning to reveal itself through the light of star formation. But this is still just the beginning. These first stars, for all their brilliance, are still incredibly rare. The universe is still mostly dark, still mostly empty, still mostly made of hydrogen and helium. The real construction work, the formation of galaxies as we know them, the creation of planetary systems, the emergence of life, all of that lies ahead. Yet already, in the light of these first stellar beacons, we can see the promise of everything that's to come. Every heavy element that will ever exist is being forged for the first time. Every galaxy that will ever shine is having its foundation laid in these first star-forming regions. Every planet that will ever orbit a star is having its raw materials created in these primordial nuclear furnaces. The Dark Ages are ending, and cosmic dawn has arrived. The universe has learned how to make light, and with that light comes the possibility of everything else: chemistry, complexity, planets, and eventually, life itself. The first chapter of the universe's story was about creating space, time, and the simplest atoms. This chapter is about learning to create everything else. As we watch these first stars burn in their lonely dark matter halos, scattered like distant lighthouses across the cosmic ocean, we're witnessing one of the most important transitions in the history of everything. The universe is waking up, beginning to shine, starting to create the rich inventory of elements that will make all future beauty possible. The first light has broken through the cosmic darkness, and nothing will ever be the same again. 9 hours have passed on our cosmic clock, and the universe has entered what might be called its most productive period, a 6-hour stretch during which the scattered lights of the first stars begin to organize themselves into the grand structures we call galaxies. If the previous epochs were about laying foundations and creating raw materials, this is when the universe truly begins to build. Imagine the cosmos at this moment as a vast construction site where an impossibly patient architect has spent billions of years preparing blueprints, gathering materials, and setting up scaffolding. The dark matter web provides the invisible framework. The first stars have begun producing heavy elements, and now, finally, the real construction work can begin. What emerges over the next few billion years will be some of the most beautiful and complex structures in the known universe. The process begins modestly enough. Those first population 3 stars burning bright and brief in their dark matter halos have done more than just illuminate the cosmic darkness. They've fundamentally changed the neighborhoods around them. Their intense ultraviolet radiation, their powerful stellar winds, and their explosive deaths have stirred up and heated the gas in their vicinity, creating bubbles of hot, turbulent material that will play a crucial role in what happens next. When the next generation of stars begins to form, they're working with different raw materials. The pristine hydrogen and helium of the early universe is now laced with traces of heavier elements: carbon, oxygen, silicon, iron, created in the nuclear furnaces of those first stellar giants. These heavy elements, astronomers' so-called metals, act like cosmic seasoning, changing the flavor of everything that follows. With even tiny amounts of heavy elements present, gas clouds can cool much more efficiently. Carbon and oxygen atoms are particularly good at radiating away heat, allowing collapsing clouds to reach much higher densities before pressure stops the collapse. This means that instead of forming only massive giants like the population 3 stars, the universe can now create a whole range of stellar sizes, including smaller, longer-lived stars that will burn steadily for billions of years. This is the birth of what astronomers call population 2 stars, and they represent a fundamental shift in cosmic demographics. While the first stars were like brilliant fireworks, spectacular but brief, these new stars are more like steady campfires, providing consistent light and warmth for cosmic ages to come. Our own sun, born much later in cosmic history, belongs to an even younger generation called Population 1, enriched with heavy elements from many generations of stellar evolution. As we move through hours 9 and 10 on our cosmic clock, these population 2 stars begin to cluster together in the deepest gravitational wells of the dark matter web. The process is driven by what physicists call hierarchical merging, smaller structures gradually combining to form larger ones, like streams flowing together to form rivers, which join to create mighty waterways. Picture this cosmic choreography unfolding over hundreds of millions of years. Small groups of stars, each group nestled within its own dark matter halo, are drawn together by gravity's patient pull. When two such groups approach each other, they don't collide like billiard balls. Instead, they perform a slow gravitational dance, spiraling around each other for millions of years before finally merging into a single larger system. During these mergers, something beautiful and chaotic happens. The orderly structure of each individual group gets stirred up, with stars flung into new orbits, gas clouds compressed and heated, and sometimes triggered into furious bursts of new star formation. It's like watching two flowing streams converge. There's turbulence and mixing at the confluence, but the result is a larger, more powerful river. This is how the first true galaxies begin to take shape, not as single, coherent structures that form all at once, but as the accumulated result of countless mergers between smaller groups of stars and dark matter. Each galaxy is like a cosmic family tree, with each branch representing a merger event that added new stars, new gas, and new gravitational mass to the growing system. As hour 11 approaches, some of these growing galaxies reach a critical size where something extraordinary happens at their centers. The supermassive black holes that began as seeds during the first star formation epoch have been growing steadily, fed by the gas and occasional stars that venture too close to their event horizons. When a galaxy becomes large enough to funnel significant amounts of material toward its central black hole, that black hole can suddenly blaze to life as what we call a quasar. Quasars are among the most energetic objects in the universe. Supermassive black holes surrounded by swirling accretion disks of superheated matter that shine brighter than entire galaxies. When matter falls toward a black hole, it heats up to millions of degrees and emits tremendous amounts of energy across the entire electromagnetic spectrum. A single quasar can outshine 100 billion stars, making it visible across billions of light-years of space. These cosmic lighthouses serve as beacons throughout the early universe, so bright they can be seen by our telescopes even today, more than 13 billion years after they first ignited. But they're more than just spectacular light shows. They're also cosmic sculptors, using their intense radiation and powerful jets to shape the galaxies around them, regulating star formation and influencing the distribution of gas across vast distances. During hours 11, 12, and 13 on our cosmic clock, the universe reaches what astronomers call the peak epoch of star formation. This is when more stars are being born per year than at any other time in cosmic history. The combination of abundant gas supplies, efficient cooling thanks to heavy elements, and the gravitational organization provided by the growing dark matter web creates ideal conditions for stellar nurseries throughout the cosmos. Galaxy formation. During this period is a messy, energetic process. Unlike the grand, ordered spiral galaxies we see in the local universe today, these early galaxies are often irregular, chaotic systems where gas streams in along dark matter filaments, triggering bursts of star formation that can light up entire regions with the blue glow of young, massive stars. These galaxies are growing quickly, doubling their stellar mass in just a few 100 million years. The heavy elements produced by this intense star formation don't stay locked up in stars forever. Stellar winds from massive stars, and especially the explosive deaths of these stars as supernovae, blow much of this enriched material back into the surrounding gas. Over millions of years, this creates what astronomers call galactic chemical evolution, a gradual enrichment of the gas from which future generations of stars will form. This process creates a beautiful feedback loop. Each generation of stars produces heavy elements that make it easier for the next generation to form and survive. Carbon and oxygen help gas clouds cool and fragment. Silicon and iron eventually become the building blocks of rocky planets. Heavier elements like gold and uranium, forged in the most violent stellar explosions, add exotic spices to the cosmic recipe. As we approach hour 14, the cosmic web becomes increasingly visible as galaxies trace out its structure with their light. What had been invisible dark matter scaffolding is now outlined in stars, revealing the universe's large-scale architecture in all its intricate beauty. Long filaments of galaxies stretch across hundreds of millions of light-years, connected at nodes where the largest galaxy clusters are forming. These galaxy clusters represent some of the largest gravitationally bound structures in the universe. They're like cosmic cities where hundreds or even thousands of galaxies have come together under the influence of their collective gravity. Within these clusters, galaxies move at speeds of thousands of kilometers per second, held in orbit around the cluster's center by the gravity of both visible matter and the much more abundant dark matter. The formation of these massive structures represents a triumph of gravity over the universe's expansion, while space itself continues to expand, carrying distant galaxies away from each other. Within these dense regions, gravity has become strong enough to overcome that expansion and pull matter together into increasingly complex arrangements. During this great construction period, the universe also develops its characteristic hierarchy of structures. Individual stars are bound together by gravity into galaxies. Galaxies cluster together into galaxy groups and clusters. These clusters are connected by filaments of the cosmic web, creating a vast network that spans the observable universe. And threading through it all is the dark matter, 5 times more abundant than ordinary matter, providing the gravitational skeleton that supports all the visible structure. There's something deeply satisfying about watching this cosmic architecture emerge from the initial simplicity of the early universe. It's like watching a city grow from scattered settlements into a complex metropolitan area, complete with neighborhoods, business districts, transportation networks, and centers of activity. The universe during this period is learning how to organize itself on increasingly grand scales. Ancient mythologies often spoke of cosmic construction projects, great works of architecture that organize the chaos of primordial creation into the ordered world we inhabit. The Mayan concept of the world tree connecting different realms of existence, the Hindu Mount Meru serving as the cosmic axis around which everything revolves, the Norse Yggdrasil supporting the 9 worlds of creation. These mythic images capture something profound about what's happening during this epoch of cosmic history. The universe is indeed building a great architecture, creating structures so vast and complex that they dwarf any human construction project. But unlike mythic architecture built by gods or giants, this cosmic construction emerges naturally from the patient work of physical forces, gravity pulling matter together, nuclear fusion forging new elements, electromagnetic radiation shaping the flow of gas and the formation of stars. The cosmic web that emerges during this period has a beauty that echoes patterns found throughout nature. Its filamentary structure resembles neural networks in the brain, the branching of rivers and their tributaries, the web of fungal mycelium connecting forest ecosystems. There seems to be something fundamental about network structures, something that emerges naturally when complex systems organize themselves over time. As hour 15 approaches on our cosmic clock, this great construction phase reaches its peak. The universe is transformed from a simple collection of hydrogen and helium atoms into a complex ecosystem of galaxies, stars, and increasingly heavy elements. The periodic table, which began with just 3 entries during the Dark Ages, now includes dozens of elements, with more being created every moment in stellar cores and explosive stellar deaths throughout the cosmos. But even as we celebrate these achievements, we can sense that the universe is preparing for its next great transition. The rapid star formation of this epoch is consuming the available gas supply in many galaxies. The energetic feedback from massive stars and supermassive black holes is heating gas to temperatures where it becomes difficult to form new stars. The universe's peak period of star formation is coming to an end. What lies ahead is a more mature phase of cosmic evolution, where the frantic construction work of these billions of years gives way to something more refined and stable. Galaxies will continue to grow through mergers, but more gradually. Star formation will continue, but at a steadier, more sustainable pace. And in at least some corners of the universe, conditions will become stable enough for an entirely new kind of complexity to emerge. The formation of planetary systems where the chemistry of life might find a foothold. The Great Construction Period has accomplished something remarkable. Starting with nothing but hydrogen, helium, and dark matter, the universe has built galaxies containing billions of stars, enriched space with heavy elements, created supermassive black holes, and established the cosmic web that will serve as the framework for all future evolution. As we watch the last moments of hour 15 tick by on our cosmic clock, we're witnessing the end of the universe's childhood and the beginning of its adolescence. The basic architecture is now in place. The tools and materials for more sophisticated projects have been created and distributed throughout space. The stage is set for the next chapter in the cosmic story, a chapter that will eventually include the formation of our own solar system and, in time, the emergence of life itself. The Great Construction Project is nearing completion, but the most interesting applications of its achievements are still to come. 15 hours have passed on our cosmic clock, and the universe has entered what might be called its golden age of stellar alchemy. If you've ever wondered how the calcium in your bones, the iron in your blood, and the gold in your jewelry came to exist, this is the chapter of cosmic history where those elements are being forged for the first time. The universe has become a vast laboratory where stars serve as nuclear furnaces, patiently transforming the simple hydrogen and helium of the early cosmos into the rich inventory of elements that will eventually make planets and life possible. Imagine the cosmos at this moment as the workshop of the most patient craftspeople imaginable. For the past several billion years, stars have been learning to build atoms, element by element, from the inside out. What began with the universe's simplest ingredients, those lonely protons and neutrons left over from the Big Bang, is being transformed into an increasingly sophisticated chemical library that would make any earthly laboratory envious. The process is taking place in stellar cores throughout the universe, where temperatures and pressures reach levels that would make the early moments after the Big Bang seem almost comfortable. Deep within these stellar furnaces, temperatures soar to hundreds of millions of degrees, and pressures become so intense that atomic nuclei, normally reluctant to get anywhere near each other, are forced into intimate contact. Here's where stars reveal themselves to be the universe's most accomplished nuclear engineers. In the core of a typical star, hydrogen nuclei are being fused into helium through a process so elegant it almost seems choreographed. 4 hydrogen nuclei perform an intricate dance, mediated by the weak nuclear force and a few helper particles, eventually combining to form one helium nucleus, with a small amount of mass converted directly into energy, according to Einstein's famous E equals mc squared. This is the nuclear reaction that powers our sun and most of the stars visible in our night sky. It's a remarkably efficient process, so efficient that the hydrogen fuel in a star's core can keep the nuclear fires burning for billions of years. But helium is just the beginning of the story. Once a star has converted enough of its core hydrogen into helium, the nuclear alchemy becomes far more interesting. As hydrogen becomes scarce in the stellar core, the nuclear fires begin to die down, and gravity, patient gravity, always waiting in the wings, begins to compress the core even further. As the compression continues, temperatures rise even higher, eventually reaching the point where helium nuclei themselves can be fused together. This is where the universe begins to create its first heavy elements in significant quantities. The fusion of helium is a more delicate process than hydrogen fusion. It requires 3 helium nuclei to come together almost simultaneously, a nuclear coincidence so unlikely that it seems miraculous it happens at all. When 3 helium nuclei do manage to find each other at exactly the right moment, they form carbon-12, the foundation of all organic chemistry. This process, called the triple alpha process after the helium nuclei's designation as alpha particles, is so finely tuned that if the nuclear physics were even slightly different, carbon would never form in significant amounts. The creation of carbon opens up an entire new chapter in stellar nuclear synthesis. Carbon nuclei can capture additional helium nuclei to form oxygen, neon, magnesium, and silicon. Each step in this process requires higher temperatures and pressures, driving the evolution of massive stars through a series of nuclear burning phases that read like a cosmic recipe book, hydrogen burning, helium burning, carbon burning, neon burning, oxygen burning, and finally, silicon burning. During silicon burning, the final stage of nuclear fusion in a star's core, the temperature reaches over 3 billion degrees, hot enough that photons themselves carry enough energy to break apart atomic nuclei. In this inferno, silicon nuclei are gradually built up into iron, cobalt, and nickel through a complex process that involves both fusion and photodisintegration. The star's core becomes a nuclear forge operating at the very limits of what's physically possible. But here's where stellar alchemy encounters a fundamental roadblock. Iron 56, with its 26 protons and 30 neutrons, represents a kind of nuclear sweet spot, the most stable configuration possible for an atomic nucleus. You can't extract energy by fusing lighter elements into iron, and you can't extract energy by breaking iron apart into lighter elements. Iron is where nuclear fusion reaches its dead end. For a massive star, reaching this iron dead end is like a cosmic death sentence. Without nuclear fusion to provide the outward pressure that balances gravity's inward pull, the stellar core begins to collapse. And when we say collapse, we mean one of the most rapid and violent events in the universe. The core of a massive star, containing more mass than our entire sun, collapses from the size of Earth to the size of a city in less than a second. The collapse is so violent that it rebounds, sending a shockwave racing outward through the star at thousands of kilometers per second. This is the birth of a supernova, one of the most energetic events in the cosmos, capable of outshining an entire galaxy of 100 billion stars. For a few weeks, a single exploding star can emit more energy than our sun will produce in its entire 10 billion year lifetime. But supernovae do more than just provide spectacular light shows for cosmic observers. The extreme conditions during a supernova explosion, temperatures of billions of degrees and pressures that defy imagination, create the perfect environment for forging elements heavier than iron. This is where the universe creates its gold, silver, platinum, and uranium, elements that require so much energy to form that only the most violent stellar explosions can produce them. The process is called rapid neutron capture, or the R process, and it's like nuclear fusion on steroids. In the intense neutron flux of a supernova explosion, atomic nuclei are bombarded with so many neutrons that they can't beta decay fast enough to keep up. Heavy neutron-rich isotopes are created that would never exist under normal circumstances, and these eventually decay into the stable heavy elements we find throughout the universe today. This is where we encounter one of the universe's most poetic ironies. The violent death of a star is what allows elements essential for life to exist. The calcium in your bones was forged in the nuclear fires of a dying star. The iron in your hemoglobin was created in a supernova explosion that occurred billions of years before our solar system existed. The gold in your jewelry was born in one of the most violent events the universe can produce. But supernovae are not the only cosmic element factories. In recent years, astronomers have discovered that neutron star collisions, events called kilonovae, are responsible for creating many of the universe's heaviest elements. When two neutron stars, each containing more mass than our sun compressed into a sphere only about 20 kilometers across, spiral into each other and merge, the result is a cosmic alchemy lab that specializes in precious metals. The neutron-rich material ejected during these collisions undergoes rapid neutron capture processes that create elements like gold, platinum, and rare earth metals. A single kilonova can produce more gold than all the supernovae in a galaxy combined. These cosmic crashes are so violent that they create ripples in space-time itself, gravitational waves that we can now detect with instruments here on Earth. As we move through hours 16, 17, and 18 on our cosmic clock, this stellar alchemy is happening throughout the universe on an unprecedented scale. The peak epoch of star formation means that more massive stars are living and dying than at any other time in cosmic history. Each stellar death disperses newly forged elements into the surrounding space, gradually enriching the interstellar medium with a chemical complexity that will make future generations of stars and planets far more interesting than their predecessors. This process of galactic chemical evolution is beautifully gradual. The first generation of stars, those population 3 giants we met earlier, were made of pure hydrogen and helium. Their deaths enriched space with the first traces of heavier elements. The second generation, population 2 stars, formed from gas that was perhaps 0.1% heavy elements by mass. Each subsequent generation forms from material that's slightly more enriched, creating a slow but steady increase in cosmic metallicity over billions of years. Different elements are produced by different types of stellar events, creating a complex cosmic supply chain. Oxygen, the third most abundant element in the universe, comes primarily from massive stars that explode as supernovae. Carbon, the foundation of organic chemistry, is produced both in the helium-burning cores of intermediate mass stars and dispersed when those stars shed their outer layers as planetary nebulae. Nitrogen, essential for amino acids and DNA, requires a more complex nucleosynthesis pathway involving carbon and oxygen as catalysts. The ancient alchemists dreamed of transmuting base metals into gold, seeking the philosopher's stone that could accomplish this magical transformation. They never could have imagined that the universe itself is the ultimate alchemical laboratory, with stars serving as philosopher's stones that can transmute simple hydrogen into every element in the periodic table. The medieval alchemists failed because they were working at far too small a scale and with far too little energy. To create gold from lighter elements, you need the nuclear furnaces of dying stars or the unimaginable violence of neutron-star collisions. The distribution of elements throughout the cosmos tells the story of this stellar alchemy. Hydrogen and helium, forged in the first few minutes after the Big Bang, still make up about 98% of all the atoms in the universe. The remaining 2%, every other element in the periodic table, has been created through billions of years of stellar nuclear synthesis. This 2% includes all the elements that make rocky planets possible, all the elements essential for life, and all the rare metals that make our technology possible. Ancient philosophies often spoke of the fundamental elements from which all things are made. The Greeks proposed 4: earth, air, fire, and water. Chinese philosophy added a 5th, metal. Hindu tradition speaks of 5 cosmic elements: earth, water, fire, air, and space. These classical element systems capture something profound about the way matter organizes itself, but they couldn't have anticipated the true complexity of cosmic chemistry. The universe's actual periodic table contains over 100 elements, each with its own nuclear architecture, its own formation pathway, and its own role in the cosmic story. Some, like hydrogen and helium, have been around since the universe's childhood. Others, like technetium, are so unstable that they can only be created artificially or in the most extreme stellar environments. Still others, like the super-heavy elements that physicists create in particle accelerators, exist for only fractions of a second before decaying into lighter species. As hour 19 approaches on our cosmic clock, the universe has become a remarkably sophisticated chemical system. The pristine hydrogen and helium gas that filled the cosmos during the Dark Ages has been seasoned with increasingly complex mixtures of heavy elements. In some regions of space, particularly in the centers of galaxies, where star formation has been most intense, the metallicity has increased to levels approaching what we see in our own solar neighborhood today. This chemical enrichment creates a beautiful feedback loop throughout cosmic history. As heavy elements become more abundant, they make it easier for gas clouds to cool and fragment, leading to more efficient star formation. They also make it possible for a wider variety of stellar types to form, from low-mass red dwarfs that will burn for trillions of years, to intermediate mass stars that will shed their outer layers as beautiful planetary nebulae. The heavy elements also enable new types of cosmic chemistry. In the dense, cool regions of interstellar space, carbon atoms can link together to form complex organic molecules. Water, methane, ammonia, and even amino acids have been detected in the space between stars. The cosmic chemistry set that began with just hydrogen and helium has expanded to include thousands of different molecular species. But perhaps most importantly, the abundance of heavy elements makes it possible for something entirely new to happen in the universe, the formation of rocky planets. For the first few billion years of cosmic history, planets could only be gas giants like Jupiter, formed primarily from hydrogen and helium. But once stellar nucleosynthesis has created sufficient quantities of silicon, iron, magnesium, and other rock-forming elements, a new type of world becomes possible. Small, dense, rocky planets with solid surfaces where entirely new types of chemistry might unfold. As we approach hour 20 on our cosmic clock, we're witnessing the end of the universe's adolescence and the beginning of its maturity. The frantic pace of star formation is beginning to slow as gas supplies in many galaxies become depleted or heated by stellar feedback. But the chemical legacy of this epoch will persist for the rest of cosmic history. Every atom heavier than lithium in your body was forged in the nuclear fires of long-dead stars, created through billions of years of stellar alchemy. The universe has learned to create complexity from simplicity, to build elaborate nuclear architectures from the most basic building blocks. It has written the periodic table in stellar cores and distributed that knowledge throughout the cosmos through the explosive deaths of massive stars. The stage is now set for the next chapter in the cosmic story, one where these heavy elements will come together on the surfaces of rocky worlds, where chemistry will give way to biochemistry, and where the universe will take its next great step toward complexity and consciousness. The stellar alchemists have done their work. The elements of life now exist, scattered throughout space, waiting to be gathered into worlds where their true potential can finally be realized. 20 hours have passed on our cosmic clock, and something wonderful is stirring in a quiet corner of what will someday be called the Milky Way galaxy. In a relatively unremarkable spiral arm, where the stellar alchemy of the past few billion years has enriched the local gas with just the right mixture of heavy elements, a particular cloud of dust and gas is beginning to feel the gentle tug of its own gravity. This isn't just any dust cloud, mind you. This is a cloud with a future that includes rocky planets, liquid oceans, and eventually curious beings who will look up at the night sky and wonder how they came to be. But right now, 4.6 billion years ago in cosmic time, it's simply a cold, dark nebula about a light year across, drifting slowly through space with no obvious indication of the drama about to unfold. Picture this stellar nursery as it existed then, a wispy collection of hydrogen and helium left over from the Big Bang, seasoned with the heavy elements created by generations of dying stars. There's carbon from the helium-burning cores of intermediate mass stars, oxygen from supernovae, silicon and iron from the explosive deaths of massive stellar giants, and even traces of gold and platinum from ancient neutron star collisions. The universe has spent 9 billion years preparing this cosmic recipe, and now it's finally ready to cook up something special. The transformation begins slowly, as all the most important cosmic events do. Perhaps a nearby supernova sends a shockwave through the nebula, or maybe a passing star gives it a gravitational nudge. Whatever the trigger, our solar nebula begins to collapse under its own gravity, spinning faster as it contracts like a figure skater pulling in her arms. As the cloud collapses, something beautiful happens. The random motion of gas and dust begins to organize itself, and the nebula flattens into a disk with most of the mass concentrated at the center. This disk is where all the action will take place, where our sun will ignite, where planets will form, and where the raw materials for billions of years of geological and biological evolution will be assembled for the first time. At the center of this disk, where material is falling in from all directions, temperatures and pressures begin to rise. The gravitational energy of all that infalling matter gets converted to heat, and after about 50 million years of this cosmic compression, something magical happens. The temperature at the center reaches 10 million degrees Kelvin. Hydrogen nuclei overcome their natural reluctance to get close to each other, and nuclear fusion ignites. Our sun is born. It's hard to overstate what a remarkable moment this is in cosmic history. Here, in this ordinary patch of space, the universe has managed to create its most important star, at least from our perspective. Not the most massive star, certainly not the brightest, but the one star in all the cosmos that will nurture the development of life as we know it. The sun that will shine on the first stirrings of chemistry in tidal pools, the sun that will warm the first leaves to photosynthesize, the sun that will light the way for curious minds to eventually understand their own cosmic origins. But the sun, for all its importance, is only part of the story. The real magic is happening in the disk of material surrounding our newborn star. This is where the heavy elements created by billions of years of stellar alchemy are about to fulfill their cosmic destiny by assembling themselves into planets. The process begins with dust, tiny grains of silicate and metal that are drifting through the solar nebula like cosmic snow. These grains, each smaller than the particles in cigarette smoke, begin to stick together when they collide. Electrostatic forces help them cling to each other, building up fluffy aggregates that look more like dust bunnies than the building blocks of worlds. As these dust aggregates grow larger, gravity finally becomes strong enough to play a role. Particles of dust and ice begin to clump together into objects the size of pebbles, then boulders, then small asteroids. This is a slow process, requiring millions of years of patient accumulation, but the result is the formation of planetesimals, rocky and icy bodies ranging from a few kilometers to a few hundred kilometers across. Now comes the really violent part. Once you have a disk full of planetesimals, they begin to collide with each other in a cosmic demolition derby that makes any earthly car crash look like a gentle bumper tap. Some collisions shatter both objects into fragments, others result in one planetesimal capturing another, gradually building up larger and larger bodies through a process called accretion. The inner regions of the solar system, where temperatures are high enough to vaporize ice, become dominated by rocky planetesimals made primarily of silicate minerals and metals. These will eventually become Mercury, Venus, Earth, and Mars, the terrestrial planets, small and dense and warm enough that any water must exist as liquid or vapor rather than ice. Further out, Beyond what astronomers call the frost line, temperatures are cold enough for water to freeze into solid ice. Here, planetesimals can grow much larger because they have access to both rocky materials and water ice. And in the outer solar system, there's a lot more water than rock. These icy planetesimals will eventually become the cores of the giant planets: Jupiter, Saturn, Uranus, and Neptune. Jupiter, forming in the sweet spot where ice becomes abundant, but the Sun is still close enough to provide substantial gravitational organization, becomes a true monster. Once its core reaches about 10 times the mass of Earth, it becomes massive enough to gravitationally capture hydrogen and helium directly from the solar nebula. Jupiter grows rapidly into a gas giant with more mass than all the other planets combined, so massive that it almost became a second star, falling just short of the critical mass needed to ignite nuclear fusion in its core. But among all these forming worlds, one stands out as particularly special: the third planet from the Sun, orbiting at just the right distance for liquid water to exist on its surface. Earth begins as just another rocky planetesimal, but it happens to form in what astronomers call the Goldilocks zone, not too hot, not too cold, but just right for the chemistry of life. Earth's early history is violent beyond imagination. The planet grows through countless collisions with asteroids and comets, each impact adding mass but also tremendous heat. The early Earth is a hellish world with a surface temperature hot enough to melt rock, an atmosphere of toxic gases, and no water oceans. The Moon doesn't exist yet. That comes later through one of the most dramatic events in our planet's history. About 50 million years after the solar system begins forming, when Earth has grown to roughly 90% of its current size, it experiences a collision that makes all previous impacts seem like gentle taps. A Mars-sized planetesimal, which scientists have named Theia after a Greek titaness, strikes the Earth in a glancing blow that partially vaporizes both objects and hurls enormous amounts of molten rock into orbit around our wounded planet. The debris from this cosmic catastrophe gradually coalesces into the Moon, our constant companion, whose gravitational influence will eventually help stabilize Earth's rotation and create the tides that may have been crucial for the development of life. The Moon that will inspire poets and lovers, that will guide sailors across dark oceans, that will be the first destination for humans venturing beyond their home planet. All of this begins with violence so extreme it almost destroys the Earth entirely. After this dramatic birth, Earth begins the long process of cooling and stabilization. Water, delivered by countless comets from the outer solar system during a period called the Late Heavy Bombardment, begins to condense from the atmosphere and collect in the low-lying areas of the planet's surface. The first oceans form, not the clear blue waters we know today, but hot acidic seas under a thick, cloudy atmosphere that would be utterly toxic to any modern life form. And yet, in these harsh conditions, something extraordinary begins to happen. The heavy elements created by billions of years of stellar nucleosynthesis, now concentrated on the surface of a rocky planet with liquid water, begin to experiment with chemistry in ways that had never been possible before in the universe's history. This is where the cosmic story becomes truly remarkable. For nearly 10 billion years, the universe had been creating increasingly complex atoms through stellar nucleosynthesis, but those atoms remained relatively simple in their interactions. Now, for the first time, conditions exist where carbon can link with other elements to form long, complex molecules, where chemistry can give way to biochemistry, where information can be stored in molecular structures and passed from one generation to the next. The emergence of life on Earth, and we're still not entirely sure how it happened, represents one of the most profound transitions in cosmic history. For the first time since the Big Bang, the universe creates structures that can make copies of themselves, that can evolve and adapt, that can process information about their environment and respond to it in sophisticated ways. Whether life began around hydrothermal vents on the ocean floor, in warm tidal pools, or perhaps even in space itself and was delivered to Earth by comets, the result is the same. The universe suddenly becomes capable of something entirely new. Matter organizes itself into patterns so complex that they become aware of their own existence. The early life on Earth is simple by our standards. Bacteria and archaea, single-celled organisms that live in environments we would consider extreme. But these humble microbes begin to transform the planet in ways that make all future evolution possible. Some learn to capture energy from sunlight through photosynthesis, using carbon dioxide from the atmosphere and water to build organic molecules, releasing oxygen as a waste product. This oxygen, initially toxic to most life forms, begins to accumulate in Earth's atmosphere through what scientists call the Great Oxygenation Event. It's a planetary catastrophe for the oxygen-intolerant organisms that dominated early Earth. But it creates opportunities for new types of life that can use oxygen to extract energy from organic molecules much more efficiently. The oxygenation of Earth's atmosphere also creates the ozone layer that protects the surface from harmful ultraviolet radiation, making it possible for life to eventually colonize the land. It changes the chemistry of the oceans and the composition of rocks at Earth's surface. In a very real sense, life becomes a geological force, reshaping the planet on which it lives. As we approach the final hours of our cosmic day, Earth undergoes a series of dramatic changes that set the stage for the emergence of complex life. Plate tectonics begins, driven by the heat of radioactive decay in Earth's interior, constantly recycling the planet's surface and helping to regulate its climate over geological time. The Moon's gravitational pull creates tides that may help drive the evolution of life from ocean to land. Through processes we still don't fully understand, some cells learn to live inside other cells, creating the first complex cells with nuclei and specialized organelles. These eukaryotic cells can eventually band together to form multicellular organisms, the ancestors of plants, animals, and fungi. The stage is set for an explosion of biological creativity that will fill every available niche on Earth with living things. But this biological revolution is still in the future, as hour 23 approaches on our cosmic clock. For now, Earth remains a microbial world where the most complex life forms are single cells, or perhaps simple colonies of cells working together. The planet looks nothing like the green and blue marble we know today. The continents are barren rock, the atmosphere is still alien, and the oceans teem with microorganisms we would find utterly foreign. And yet, the fundamental breakthrough has already occurred. The universe has learned to make life. After nearly 14 billion years of physical and chemical evolution, matter has finally organized itself into patterns capable of growth, reproduction, evolution, and eventually consciousness. The pale blue dot that will someday be home to poets and scientists, to whales and redwood trees, to music and mathematics, has begun its biological journey. Ancient creation myths speak of the emergence of life from the union of earth, air, fire, and water, and in a sense they captured something profound about what happened during this epoch. The rocky materials of Earth, created through stellar nucleosynthesis, the water of the oceans delivered by comets, the energy of sunlight from our newly ignited star, and the thin atmosphere gradually transformed by living organisms themselves, combine to create conditions where life can emerge and flourish. The Hindu concept of Prithvi, the Earth as Divine Mother, reflects the deep truth that our planet is not just a passive stage where life performs, but an active participant in the evolutionary process. Earth and life have evolved together, each shaping the other in a cosmic dance that continues to this day. As hour 23 draws to a close, we find ourselves on the threshold of the most remarkable chapter in our cosmic story. The universe has spent over 13 billion years preparing for this moment, creating space and time, forging the elements, building galaxies and stars, assembling planets and moons. All of this patient preparation has led to the emergence of a small, wet, rocky world where chemistry has learned to become biology. Our pale blue dot has appeared in the cosmic darkness, and with it comes the possibility of everything we know and love, the possibility of minds that can contemplate the universe that created them, of beings who can look back through deep time and trace their ancestry to the first stars, of consciousness arising from matter and energy to become aware of its own cosmic origins. The stage is set for the final, most dramatic moments of our cosmic day. We're now approaching the final 2 minutes of our cosmic day, and something extraordinary is about to unfold on that pale blue dot we watched form in the previous chapter. For nearly 4 billion years, most of Earth's existence, life has been experimenting quietly with different ways of being alive, mostly in the form of single-celled organisms swimming through ancient seas. But now, in these last precious moments of our cosmic timeline, life is about to discover some truly spectacular possibilities. Picture Earth as it exists at 23:58 on our cosmic clock, about 540 million years ago in real time. The planet looks almost alien compared to the world we know today. The continents are mostly barren rock with no forests, no flowers, no grass, just occasional mats of bacteria and algae clinging to shorelines. The oceans, though, are about to become the stage for one of the most remarkable biological revolutions in Earth's history. This is the moment of what scientists call the Cambrian explosion, though explosion might give you the wrong idea. We're not talking about a sudden bang, but rather like watching a fireworks display in extreme slow motion, a spectacular burst of biological creativity that unfolds over tens of millions of years. After spending most of Earth's history as single cells doing their own simple things, life suddenly discovers the concept of teamwork on a grand scale. The first hint of what's coming appeared a bit earlier, when some enterprising cells learned to stick together in organized groups. These weren't just random clusters, but structured communities where different cells took on specialized jobs. Some focused on gathering food, others on protection, still others on reproduction. It's like watching the first crude villages form after millions of years of everyone living as hermits. But the real drama begins when life discovers how to build itself some architecture. For billions of years, living things have been soft, squishy affairs, cells with flexible membranes that could change shape but couldn't build much in the way of permanent structures. Then some clever organisms figured out how to precipitate minerals from seawater, creating the first shells, the first exoskeletons, the first hard parts that could be preserved as fossils. This biological construction boom transforms Earth's oceans into something that would look almost unrecognizable to us today. Imagine snorkeling through a Cambrian sea. You might encounter a Nomalocaris, a meter-long creature that looks like someone crossed a shrimp with a science fiction monster, swimming through the water with undulating fins along its sides. Or perhaps you'd meet a trilobite, one of evolution's most successful experiments. Arthropods with compound eyes and segmented bodies, that would thrive for nearly 300 million years. There's Opabinia, with its 5 mushroom-shaped eyes and a long proboscis ending in a grasping claw that makes it look like some kind of biological vacuum cleaner. Wiwaxia, covered in scales and spines like a medieval knight's armor. Hallucigenia, so bizarre that scientists initially reconstructed it upside down and backwards, not sure which end was which. These aren't just random monsters dreamed up by evolution. They represent experiments in different ways of solving the fundamental problems of life. How do you move through water efficiently? How do you capture food? How do you avoid being eaten? How do you sense your environment? The Cambrian seas become evolution's laboratory, where life tries out countless different approaches to these challenges. What makes this explosion of diversity possible is a kind of biological arms race. Once some organisms develop hard shells for protection, others evolve better ways of cracking those shells open. Once predators become more sophisticated, prey species develop new escape strategies, better camouflage, more elaborate defensive systems. Each innovation drives counter-innovations, creating a feedback loop that accelerates the pace of evolutionary change. But perhaps the most significant development during this period is the evolution of complex sensory systems. The first sophisticated eyes appear during the Cambrian, and suddenly, being alive becomes a much more visual experience. Predators can spot prey from a distance. Prey can see predators coming. The murky, largely touch and taste world of early Earth becomes a place where creatures can perceive their environment with startling clarity. These early eyes are marvels of biological engineering. Trilobites develop compound eyes with thousands of individual lenses, each made of calcite crystal, the same mineral that forms limestone. Some species have eyes on stalks that can swivel independently. Others develop eyes that can look up toward the water's surface, while simultaneously watching for threats below. The evolution of vision fundamentally changes what it means to be a living creature on Earth. As we tick forward through the last minutes of our cosmic day, this explosion of marine diversity is followed by life's next great adventure, the colonization of land. For over 3 billion years, every living thing on Earth had been aquatic. The land surfaces were sterile rock and sand, baked by unfiltered ultraviolet radiation from the sun. But gradually life begins to venture onto the shores. The pioneers are humble, simple algae and bacteria that can tolerate brief periods out of water. But these biological beachcombers begin the slow process of creating soil, breaking down rock with acids they produce, mixing organic matter with mineral particles to create the first primitive soils. Fungi develop partnerships with early plants, trading nutrients from the soil for organic compounds produced by photosynthesis. The first true land plants appear around 2358-45 on our cosmic clock. Simple, moss-like organisms without roots, leaves or flowers. But once plants establish a foothold on land, they begin one of the most transformative processes in Earth's history. They start producing oxygen at an unprecedented rate while simultaneously removing carbon dioxide from the atmosphere. This atmospheric engineering project gradually transforms Earth's climate and creates the oxygen-rich air that will eventually make complex animal life possible. The first forests appear, not the towering trees we know today, but strange landscapes of giant ferns and primitive trees that look more like enormous asparagus spears than anything in a modern forest. Where plants go, animals follow. The first arthropods crawl out of the sea, initially just to mate or lay eggs before returning to water, but gradually spending more and more time on land. Some of these early land animals grow to enormous sizes, millipedes 2 meters long, dragonflies with wingspans like small airplanes, scorpions the size of large dogs roaming through the primitive forests. But the really dramatic changes come with the evolution of backbones. The first fish develop internal skeletons made of cartilage, then bone, giving them structural support that allows them to grow larger and swim more efficiently. Some of these fish develop primitive lungs alongside their gills, allowing them to survive in oxygen-poor water or even venture briefly onto land. Around 23:59:10 on our cosmic clock, some of these lungfish take the evolutionary leap that changes everything. They develop limbs capable of supporting their body weight on land. These early amphibians are still tied to water for reproduction. They must return to lay their eggs, but they open up entirely new ecological niches on land. The evolution of the amniotic egg around 23:59:20 liberates vertebrate life from its dependence on water. Reptiles can now reproduce entirely on land, laying eggs with shells that protect the developing embryo from drying out. This breakthrough leads to the age of dinosaurs, a period lasting over 160 million years, during which reptiles become the dominant large animals on Earth. And what a spectacular reign it is! Dinosaurs evolve into an incredible diversity of forms. Tiny feathered creatures no bigger than pigeons, massive long-necked sauropods that could look over 4-story buildings, fierce predators with teeth like railroad spikes, and bizarre species with elaborate crests, spikes, and armor plating that make them look like creatures from another planet. Some dinosaurs learn to fly, evolving into birds that colonize the skies with the same enthusiasm their ancestors showed for colonizing the land. Others return to the seas, becoming marine reptiles perfectly adapted for life in the water. Dinosaurs develop complex social behaviors, sophisticated parental care, and even primitive forms of communication. But around 23:59:35 on our cosmic clock, disaster strikes. An asteroid 6 miles across slams into Earth with a force of billions of nuclear bombs, triggering climate changes that end the age of dinosaurs. The impact throws so much dust and debris into the atmosphere that the planet enters a prolonged winter. Plants die from lack of sunlight. Food chains collapse. The great reptilian experiment comes to a sudden, violent end. Yet this catastrophe opens up new opportunities. With the dominant large animals gone, mammals, which had spent 160 million years as small, largely nocturnal creatures, suddenly find themselves in a world full of empty ecological niches. They begin what scientists call adaptive radiation, rapidly evolving into an incredible diversity of forms to fill the vacant roles in Earth's ecosystems. Some mammals learn to fly, becoming bats. Others return to the seas, eventually evolving into whales and dolphins. Some grow to enormous sizes, becoming elephant-sized ground sloths and rhinoceros-like creatures with bizarre horns and tusks. Others remain small but develop increasingly sophisticated behaviors and social structures. But the most significant mammalian development from our perspective is the evolution of enlarged brains relative to body size. Some lineages begin developing more complex nervous systems, better memory, improved problem-solving abilities, and sophisticated social behaviors. These big-brain mammals include early primates, our distant ancestors, swinging through the trees of ancient forests. As we approach 23:59:50 on our cosmic clock, these early primates are beginning to experiment with tool use, complex communication, and social cooperation that goes far beyond anything seen before in Earth's history. The stage is being set for the emergence of something entirely new in the universe, a species that can understand its own cosmic origins. Throughout this great acceleration of biological complexity, we see echoes of mythological themes that humans have always found meaningful. The tree of life appears in mythologies around the world, from Norse Yggdrasil to the Kabbalistic tree of life to the world tree of many indigenous traditions. These myths capture something profound about the branching, interconnected nature of evolution, the way all life forms are related through common ancestry. The Great Chain of Being, a medieval concept that arranged all life forms in a hierarchy from simple to complex, reflects humanity's intuitive understanding that evolution has direction, not toward predetermined goals, but toward increasing complexity and capability. Modern evolutionary biology confirms this intuition, while adding the understanding that this complexity emerges through natural processes rather than divine design. Indigenous creation stories often speak of a time when animals could speak, when the boundaries between different species were fluid, when transformation was the rule rather than the exception. The fossil record reveals that these stories capture something true about deep evolutionary time. There was indeed a period when the distinctions between different types of life were much less fixed, when evolution was rapidly experimenting with new forms and possibilities. The Aboriginal Australian concept of dreamtime, a period when the world was soft and formable, when ancestral beings created the landscape and established the rules by which life operates, parallels our understanding of these crucial periods in Earth's history when the basic patterns of life were being established. As we watch this great acceleration unfold in our cosmic day's final minutes, we witness something unprecedented in universal history. For nearly 14 billion years, the cosmos had been creating increasingly complex structures: atoms, molecules, stars, galaxies, planets. But with the emergence of complex life on Earth, the universe achieves something qualitatively new: the ability to process information, to learn from experience, to adapt and evolve in response to changing conditions. The development of sophisticated nervous systems represents another quantum leap in cosmic complexity. Brains are information processing systems more complex than any computer humans have ever built, yet they emerge naturally through evolutionary processes. A dolphin's brain processes acoustic information in ways we're only beginning to understand. An octopus solves problems with an intelligence that emerges from a nervous system organized completely differently from our own. But the most remarkable development is still to come. As our cosmic clock approaches its final seconds, one particular lineage of primates in Africa is beginning to show signs of something the universe has never seen before: the ability to understand and manipulate abstract concepts, to create and transmit complex cultural information, to imagine futures and remember pasts with unprecedented detail. These early humans are still part of the natural world, living as hunter-gatherers in small groups, using simple stone tools and fire, but they're already displaying behaviors that set them apart from all previous life forms. They're creating art on cave walls, burying their dead with ceremony, developing languages capable of infinite expression. As 23:59:58 approaches on our cosmic clock, these remarkable primates are about to embark on a journey that will transform not just their own species, but the entire planet. They're about to discover agriculture, build cities, develop writing systems, and eventually develop the scientific tools needed to understand their own cosmic origins. The great acceleration of life's complexity has brought us to the threshold of the most remarkable moment in cosmic history: the emergence of consciousness capable of contemplating the universe that created it. In the final seconds of our cosmic day, the universe is about to become aware of itself through the minds of curious primates on a small planet, orbiting an ordinary star in an unremarkable galaxy. The stage is set for humanity's cosmic moment. And here we are, in the final 2 seconds of our cosmic day, approaching the most remarkable moment in the universe's 13.8 billion year story. Everything that has come before, the birth of space and time, the forging of elements in stellar cores, the formation of galaxies and planets, the emergence and evolution of life, has been leading to this instant when the cosmos finally opens its eyes and begins to understand itself. Picture Africa around 300,000 years ago, at 23:59, 58.5 on our cosmic clock. The continent is a patchwork of forests, savannas and lakes, populated by an incredible diversity of life forms that have been millions of years in the making. Among the many species of primates swinging through the trees and walking across the grasslands, one particular group is beginning to display behaviours that would seem familiar to us today, even though they're separated from us by thousands of generations. These early humans, our direct ancestors, are already doing something no other species in Earth's history has ever done. They're creating tools not just for immediate use, but for future needs they can imagine. They're making art on cave walls that serves no obvious survival function, but somehow feels necessary. They're burying their dead with ceremony, suggesting they've developed concepts of meaning and afterlife that transcend the simple biological drives that govern other animals. But most remarkably, they're talking to each other in ways that go far beyond the communication systems of even the most sophisticated animals. They're using language not just to coordinate hunting or warn of danger, but to share stories, to pass down knowledge from one generation to the next, to imagine possibilities that don't yet exist. This capacity for abstract thought and complex communication sets the stage for everything that follows. Unlike genetic information, which changes slowly through biological evolution over many generations, cultural information can be transmitted, modified, and improved within a single lifetime. A useful technique discovered by one person can spread through an entire population in years rather than millennia. As we tick forward through these final seconds of cosmic time, human culture begins to accelerate in ways that have no precedent in natural history. Around 23:59, 59.5, about 12,000 years ago, some groups of humans discover agriculture. Instead of wandering in search of food, they learn to plant seeds, tend crops, and store surpluses for times when hunting and gathering might not provide enough. This agricultural revolution is more transformative than it might initially appear. When you can produce and store food surpluses, you can support people who don't spend all their time gathering food, specialists who can focus on making better tools, creating art, developing new technologies, or thinking about abstract questions. For the first time in Earth's history, a species creates the conditions where some individuals can spend their lives pursuing knowledge purely for its own sake. Villages grow into towns, towns into cities, cities into civilizations with complex social structures, specialized roles, and accumulated knowledge that no single individual could master in a lifetime. Writing systems emerge, first as simple record-keeping for trade and taxes, but eventually as a way to preserve and transmit the most sophisticated ideas across generations and across continents. The development of writing is perhaps as significant as the development of language itself. For the first time, human knowledge can accumulate across centuries and millennia. A scholar in ancient Baghdad can read and build upon ideas developed by philosophers in ancient Greece. An astronomer in medieval China can study observations recorded by colleagues centuries before. The individual human lifespan, previously the limit for any single mind's accumulation of knowledge, is transcended by cultures that can remember and build upon their discoveries across vast stretches of time. As 2359:59.7 approaches on our cosmic clock, roughly 2,500 years ago, something extraordinary happens. Across several different civilizations, independently and almost simultaneously, humans begin asking profound questions about the nature of reality itself. In Greece, philosophers like Democritus propose that all matter is made of tiny, indivisible particles called atoms. In India, Buddhist and Hindu thinkers develop sophisticated concepts about the impermanent nature of all phenomena. In China, Taoist philosophers contemplate the underlying principles that govern natural processes. These aren't just abstract intellectual exercises. They represent the emergence of scientific thinking, the recognition that the world operates according to patterns that can be discovered, understood, and described. For the first time in cosmic history, matter has organized itself into structures complex enough to investigate the laws that govern matter itself. The pace of discovery accelerates as human civilizations develop better tools for observing and understanding the natural world. Around 2359:59.85, about 400 years ago, Galileo points a telescope at the night sky and discovers that the Milky Way is composed of countless individual stars, that Jupiter has moons orbiting around it, that the moon has mountains and craters like a world in its own right. These observations don't just add to human knowledge, they fundamentally change how we understand our place in the cosmos. The Earth, which had seemed like the center of everything, reveals itself to be just one planet among many, orbiting an ordinary star in a galaxy containing hundreds of billions of other stars. Newton discovers that the same force that makes an apple fall from a tree also keeps the moon in orbit around Earth, and the Earth in orbit around the Sun. For the first time, humans realize that the entire universe operates according to mathematical laws that can be written down in equations and used to predict the future behavior of everything from projectiles to planets. At 2359:59.9, about 150 years ago, Darwin proposes that all life on Earth is related through common ancestry, that the incredible diversity of living things has emerged through natural processes operating over vast periods of time. Humans begin to understand that they're not separate from nature, but part of it, the latest chapter in a 3.8 billion year story of biological evolution. Then at 2359:59.95, about 100 years ago, Einstein discovers that space and time are not separate, fixed entities, but aspects of a flexible, four-dimensional fabric that can be warped by mass and energy. Quantum mechanics reveals that reality at its smallest scales operates according to principles that seem almost magical. Particles that can exist in multiple states simultaneously, that can affect each other instantaneously across vast distances, that behave differently when observed than when unobserved. These discoveries don't just satisfy human curiosity, they lead to technologies that transform civilization itself. The understanding of electromagnetism leads to electric lights, radio communication, and computers. Quantum mechanics makes possible lasers, transistors, and the digital revolution. Relativity enables GPS satellites to maintain the precise timing needed for navigation systems. At 2359:59.98, about 50 years ago, humans accomplished something that would have seemed impossible to every previous generation. They leave their home planet. Apollo astronauts walk on the moon's surface, and look back at Earth rising over the lunar horizon, a small blue marble suspended in the cosmic darkness. For the first time, representatives of terrestrial life see their home planet from the outside as a single fragile system floating in an ocean of space. The view from space changes human consciousness in ways that are still unfolding. National borders disappear when seen from orbit. The Earth reveals itself as one interconnected system, atmospheric, oceanic, and biological processes that operate on a planetary scale. The perspective gained from leaving Earth helps humans understand that they live not just in countries or continents, but on a planet that is their only home, in a universe that is mostly empty space and hostile to life as we know it. And now, at 2359.59.99, just a few decades ago, humans begin to understand their cosmic origins. Telescopes reveal that the universe itself has a history, that it began in a hot, dense state, and has been expanding and cooling for 13.8 billion years. The cosmic microwave background radiation provides a baby picture of the universe when it was only 380,000 years old. Observations of distant supernovae reveal that the expansion of the universe is accelerating, driven by a mysterious dark energy that makes up most of the cosmos. Humans discover that every atom in their bodies heavier than hydrogen was forged in the nuclear furnaces of stars that lived and died before the solar system existed. They realize that they're not just observers of the cosmic story, but participants in it, perhaps the only participants capable of understanding the full scope of what has unfolded over these 13.8 billion years. As we approach the final microsecond of our cosmic day, the present moment, humans are beginning to detect gravitational waves from colliding black holes, to image the event horizons of supermassive black holes, to discover thousands of planets orbiting other stars. They're beginning to seriously search for signs of life elsewhere in the universe, while simultaneously grappling with their responsibility as the only known life forms capable of significantly altering planetary environments. The development of artificial intelligence and genetic engineering suggests that humanity may be approaching another transition as significant as the development of language or agriculture. For the first time, a species may be gaining the ability to direct its own evolution, to create forms of intelligence that surpass biological brains, to potentially spread life and consciousness throughout the cosmos. And here's the most remarkable thing about this final second of cosmic time. It's not an ending, but a beginning. The universe has spent 13.8 billion years creating the conditions for consciousness to emerge, and now that consciousness is beginning to understand its origins and contemplate its future, the cosmos has become aware of itself through human minds, and that awareness is expanding rapidly. Ancient mythologies spoke of heroes whose journeys transformed not just themselves, but the entire world. The human journey through these final seconds of cosmic time follows this archetypal pattern on the grandest possible scale. Humanity has undertaken what Joseph Campbell would recognize as the ultimate hero's journey, leaving the comfortable realm of unconscious existence, venturing into the vast unknown of the cosmos, and returning with knowledge that transforms understanding of what it means to exist. The Promethean myth of stealing fire from the gods takes on new meaning when we realize that humans have indeed stolen the fire of the stars, not literally, but intellectually, by understanding nuclear fusion and using that knowledge to power civilization. The Tower of Babel story speaks to humanity's drive to reach toward heaven, which has now manifested as actual rockets carrying people beyond Earth's atmosphere and robotic emissaries to every planet in the solar system. Indigenous prophecies often speak of a time when humanity must choose between paths that lead to destruction or transcendence. We seem to be living in exactly such a time, possessing technologies powerful enough to either destroy our civilization or enable it to flourish for millions of years, perhaps spreading life and consciousness throughout the galaxy. Carl Sagan captured something profound about this moment when he wrote about the cosmic perspective, the recognition that humans are not separate from the universe, but the universe becoming aware of itself. Every time a human looks up at the night sky and feels wonder, every time a scientist discovers a new law of physics, every time someone contemplates the vastness of space and time, the cosmos is experiencing something entirely new: self-awareness. This perspective doesn't diminish human significance, it expands it infinitely. Humans aren't insignificant specks in an uncaring universe. They're the universe's way of understanding itself. The carbon in their bodies, forged in stellar cores billions of years ago, has organized itself into patterns complex enough to contemplate the stars where it was born. As our cosmic clock finally strikes midnight, as 24000 arrives and our cosmic day concludes, we find ourselves in the most remarkable moment in universal history. For the first time since the Big Bang, the cosmos has produced structures capable of understanding their own cosmic origins. Matter has evolved into mind, and mind has discovered the story of matter. The universe began as pure energy expanding from an impossibly hot, dense state. It cooled into particles, then atoms, then gas clouds that collapsed to form the first stars. Those stars forged heavy elements and dispersed them through space when they died. Planets formed from this enriched material. On at least one planet, chemistry became biochemistry. Life emerged and evolved, and eventually consciousness arose. And now that consciousness has traced its ancestry back to the Big Bang itself, the universe has completed a cosmic circle, beginning as pure physics and ending, at least in this corner of space, as physics becoming aware of itself through biology and neuroscience and astronomy. This is where our cosmic day ends, but it's also where the next chapter begins. Tomorrow, metaphorically speaking, humanity will continue the journey of cosmic discovery. We'll search for life on other worlds, perhaps finding evidence that consciousness has emerged elsewhere in the universe. We'll develop new technologies that might enable our descendants to travel to the stars. We'll continue unraveling the deepest mysteries of physics, perhaps discovering new laws of nature that we can't even imagine today. The cosmic day is over, but the universe is just beginning to wake up. And you, yes, you, listening to these words in the quiet of your evening, are part of that awakening. You are the cosmos becoming conscious of itself, matter organized into mind, the universe's way of experiencing wonder at its own existence. The cosmic day is complete, but before we drift into sleep, let's pause for a moment to reflect on this extraordinary journey we've taken together. And here we are, at the end of our cosmic day, having travelled together through 13.8 billion years of universal history in the span of a single evening. We've watched space and time crystallize from quantum foam, witnessed the first atoms form in the cooling aftermath of creation, seen stars ignite and die and scatter their nuclear ashes across the cosmos, marvelled at the slow assembly of galaxies and the patient formation of planets, and finally arrived at this extraordinary moment when matter has organized itself into minds capable of contemplating their own origins. It's quite a journey we've taken, isn't it? From the impossibly hot, dense singularity of the Big Bang to the quiet room where you're listening to these words, a path that encompasses everything from the fusion of hydrogen nuclei in stellar cores to the evolution of consciousness in biological brains. And perhaps the most remarkable thing about this journey is that it's not just a story we're telling about the past. It's the story of how you came to be sitting here right now, in this present moment. Every breath you take contains oxygen atoms forged in the nuclear furnaces of massive stars that exploded billions of years before our sun existed. The calcium in your bones was created through stellar nuclear synthesis in dying giant stars. The iron in your blood carries the signature of ancient supernovae that lit up primordial skies. You are quite literally made of star stuff, as Carl Sagan so poetically observed, not as a metaphor, but as a simple statement of cosmic fact. But there's something even more profound than this material connection to the cosmos. The very capacity you have to understand these connections, to feel wonder at the scale of deep time, to imagine yourself existing within this vast cosmic story. That capacity itself is perhaps the most remarkable achievement in the universe's 13.8 billion year history. Think about what had to happen for this moment of understanding to be possible. The universe had to expand and cool at exactly the right rate to allow matter to clump into structures without everything either flying apart forever or collapsing back into a singularity. The fundamental forces had to be balanced with extraordinary precision. If gravity was slightly stronger, stars would burn out too quickly. If it were slightly weaker, they would never ignite at all. The nuclear physics governing stellar fusion had to be fine-tuned to produce the heavy elements essential for rocky planets and biological chemistry. And then, on at least one of those rocky planets, chemistry had to discover how to become self-replicating. Evolution had to stumble upon increasingly sophisticated ways of processing information. And nervous systems had to develop the capacity not just to respond to immediate stimuli, but to model abstract concepts, to imagine possibilities that don't yet exist, to contemplate questions that have no obvious survival value. All of this extraordinary fine-tuning and unlikely development has led to you, sitting in this moment capable of grasping the entire sweep of cosmic history. You exist at 235959.999 on our cosmic clock, so close to the end of our cosmic day that your entire species' history occupies only the final few milliseconds. And yet, those final milliseconds represent the universe becoming aware of itself for the first time. There's something both humbling and elevating about this perspective. Humbling because it reveals just how brief human existence has been in the context of cosmic time. Our entire civilization, from the first agricultural settlements to space exploration, fits into a time span so short it barely registers on the cosmic scale. All of recorded history, every empire that has risen and fallen, every scientific discovery, every work of art, every life ever lived, occurs within the cosmic equivalent of the final tick of the second hand on a clock. Yet this perspective is also deeply elevating, because it reveals that you are not an accident or an afterthought in the cosmic story. You are the universe's way of understanding itself. Every moment of wonder you feel when looking up at the night sky is the cosmos experiencing curiosity about its own nature. Every scientific discovery is the universe learning something new about the laws that govern its own behavior. Every act of compassion or creativity is matter and energy, organized in such exquisite patterns that they can transcend their material origins and touch something that feels eternal. This doesn't mean that human existence is the ultimate purpose toward which the entire universe was aimed. That would be a rather presumptuous interpretation. The cosmos is vast beyond our comprehension, and there may be countless other forms of consciousness scattered throughout space and time that we can't even imagine. But it does mean that consciousness, wherever and however it arises, represents something genuinely new and significant in the universe's ongoing story. The emergence of minds capable of contemplating cosmic history is not just another interesting development, like the formation of the first galaxies or the appearance of multicellular life. It's a qualitative transformation in what the universe is capable of. For nearly 14 billion years, the cosmos was a purely physical system, matter and energy interacting according to the laws of physics, creating increasingly complex structures, but never stepping outside those structures to observe and understand them. With consciousness, the universe transcends its own physical boundaries in a sense. Not by violating the laws of physics, consciousness is still a physical process occurring in physical brains, but by creating systems complex enough to model reality, to form abstract concepts, to imagine counterfactuals, to feel awe and wonder and curiosity about existence itself. So as you prepare to drift off to sleep tonight, carry with you this cosmic perspective. You are not separate from the universe, observing it from the outside. You are the universe in the process of understanding itself. The wonder you feel when contemplating the vastness of space and time is the cosmos experiencing wonder at its own existence. The curiosity that draws you to seek knowledge about your origins is the universe's drive to comprehend its own nature. This perspective doesn't solve all the mysteries or answer all the questions about existence. There's still so much we don't understand. What dark matter and dark energy really are, whether consciousness can arise on other worlds, what lies beyond the observable universe, whether there are other universes with different physical laws. The cosmic day we've just experienced together represents our current best understanding of how we got here, but that understanding continues to evolve as we make new discoveries and develop new theories. What this cosmic perspective does offer is a sense of connection and meaning that transcends the usual boundaries of human experience. Your worries and hopes, your relationships and responsibilities, your daily struggles and moments of joy, none of these become less important when viewed from a cosmic perspective. If anything, they become more precious because they represent the universe's brief, remarkable experiment with consciousness and meaning. The elements in your body will outlive you, eventually returning to the cosmic recycling system to become part of future stars and planets and perhaps other living beings. But the particular pattern of matter and energy that is your consciousness, your unique way of experiencing and understanding existence, is a cosmic event that has never happened before and will never happen again. Rest well in the knowledge that you are both ancient and utterly new, ancient in your atomic ancestry that traces back to the first stars, utterly new in your capacity to understand and appreciate that ancestry. The universe has been 13.8 billion years in the making, and tonight it dreams through your dreams. The cosmic day is complete, and tomorrow, in whatever form it takes, the universe continues its patient journey toward ever greater complexity, understanding, and beauty. And you, wherever your own journey leads, will always be part of that cosmic story, a brief but essential chapter in the universe's ongoing biography. This is the sleepy astronomer wishing you clear skies, gentle starlight, and sweet dreams, my fellow stardust.